Testing 1, 2, 3. Let's update the titles. Yeah, welcome back, everyone. Um, Today we'll be continuing from where we left off. So we had loaded the 3D models, but I've also realized there seems to be some error with the new 3D models getting loaded in, and loading in like weird geometry. Yeah, we'll be trying to figure that out. Yeah. Uh, yeah, let's continue with this.
Extend the model class to be able to read in model data using the wavefront object layer struct called hash with type LVE model vertex. With this, we can now take an instance of the vertex already been added to the builder.vertices vector and store the position at which the vertex was originally added. Then scroll down to the end of the function, but still inside the for loops, and
Can say 0, 1, 2. And that was for the colors. Let me see if this fixes it. Yes, it's a bit all janky. Wait, it's 3 minus 2 0. Let me double check with the code here. Here it's 2 minus 1 0. Hmm. 3 index vertex plus 2. And else vertex color is 1. Okay, let's see the video.
replace vertices.pushback with if unique vertices.count of vertex is equal to 0.
Oh, let me just double check that the stream is working. Is it loaded on Twitch and on YouTube? Okay, Twitch has loaded. And YouTube is loaded as well. Yeah, cool.
Then unique vertices at vertex is equal to static cast uint32 type of vertices.size. Then also call vertices.pushback vertex. So what this does is if the vertex is new, we add it to the unique vertices map. Its position within the builder's vertices vector is given by the vertices vector's current size. Finally, after the if block, call indices.pushback unique vertices at vertex. With this, we add the position of the vertex to the builder's indices vector. And that's it. We can build, run, and see our base.
Yeah, if we remove the 1, it doesn't run. This kind of gets stuck. Yeah, just a blank screen. Add -1, it works. Okay, in the next tutorial they fix the color, but
more. The big difference is that
shape
the vertex
is
count has been
here.
reduced from 30,888 to just 5,500.
Let's see if it gets fixed in this one.
A lighting model is a simplification of the light transport equation, which dictates how light energy distributes, reflects, and transports within a scene. This is a complex equation that can be very expensive to solve computationally, so instead, we often rely on lighting models, which only approximate the light transport equation, but are simpler to calculate and map well to graphics hardware. One such model is the diffuse or Limburtian shading model. It makes the assumption that the surface reflects incoming light equally in all directions. This is a very basic model that works well for non-metallic, matte surfaces. This is basically the opposite of a mirror surface. With a theoretical perfect mirror, every incoming light ray is perfectly reflected with the angle of incidence matching the angle of reflection, and zero light is scattered. On the other hand, a perfect Lambertian surface would scatter an incoming light ray equally in all directions. Lambertian surfaces obey Lambert's cosine law, which states that the color of a surface is proportional to the cosine of the angle between the surface normal and the direction to the light source.
Let's see the comments. So there's no difference in calculation between 4 and 4 and 3 by 3.
Surface normal is a unit vector that's perpendicular to the plane of the surface. So this is the vector that starts on the surface and points directly away. Normals are generated by modeling software for us and provided in the mesh object file for each vertex. The dot product of two vectors a and b is equal to the length of a times the length of b times cos theta, where theta is the angle between the two.
Let me just turn on the fan. It's too hot here. It's winter and it's still hot.
Two vectors. If both vectors are normalized to be of unit length, then a dot b is equal to cos theta. Therefore, in vector form, the reflected light intensity for any outgoing direction can be calculated using the dot product of the surface normal and a normalized vector pointing to the light source. The intuition behind this equation is that as the angle between the light source direction and surface normal increases, the light is spread out over a larger area. Therefore, the outgoing light at any specific point will be of lower intensity. Scratcher Pixel has a very in-depth article going into how the derivation works out to be a cos theta relationship. So if we know the direction to a light source, we can determine the light's intensity at any given vertex on the model by using the normal at that vertex. Okay, let's get to coding. First, let's fix a mistake from last week. In the load model function of the model implementation file, my method for setting the default color doesn't actually work. This is because the trib.colors vector is always initialized to be the same size as the trib.vertices vector, and filled in with ones wherever a color is not provided in the wavefront file. So this entire block of code can be simplified. I'll remove the current implementation and then simply duplicate
Control C, Control V. And V colors that out, shift out. And vertex colors. Colors and vertex index.
when no color is specified. Okay, now last week we added the normal and UV fields to the vertex struct, but we haven't yet provided these attribute values to a shader. So let's fix that. Just above it, the default color being white when no color is specified. A color, above. I'll remove the current implementation and then simply duplicate the lines above. Change vertex.position to vertex.color
Vertex.color.
and a trib.vertices to a trib.colors. This will work the same as before with the default color being white when no color is specified. Okay, now
Does this work better? Hmm. I also like glitched out. But he isn't checking with this. So yes. Smooth. Yes. Yeah. Let's try it now.
week, we added the normal and
Yeah, this is straight.
UV fields to the vertex struct, but we haven't yet provided these attribute values to a shader. So let's fix
Did I add something unnecessary? Let me check.
Welcome back. In this video, we are going to move past the simple 3D cube and extend the model is just painted white. To get something with visible detail, we need to apply lighting, which we'll do so in next week's tutorial. So we've successfully my Windows machine. Build and run your code, and we get a rainbow colored cube. That's because each vertex only specifies one color, and then the fragmental. But in practice, now. And there we go. In the device and models.
Let's see. First up, CPP. Create model from file.
/colorcube.obj. Note that this is a relative path. If you run into an error, try using an absolute file path instead. For example, this is what I use on my Windows.
Let's see. Database.
Build and run your code, and we get a rainbow.
Create game object. Then batch. It's not doing a move anymore. Only model. Game object model. Okay, we cannot move anything. Game object model.
Because each vertex.
Let's start. That's building. No, it's still glitchy.
Is one color, and then the
Let's see. Is there something wrong with this? Perhaps. Let me check in the comments. If anyone is getting LIM 2019 error, should be tiny object loader. It should be tiny obj loader implementation. Okay. And each vertex delete and just to
just like in tutorial 7. If we wanted a model to look like the previous 6 colored cube we had, we would need to duplicate each vertex position twice so that we could.
Right, where are we using this? Are we utils? Hash combine. Control F, size T. Static cast size T.
Different color per face. Now let's try a more complex model. Update the file path to load. So first let's create a new file called lveutils.hpp. I've included this function in a paste bin link below. This is a function that can combine an arbitrary number of hash values together. Hash functions are kind of a complex topic, and I assume most of you guys are
Void hash combine size T, seed, const TNV, const just, std hash T. This we have magic number, and hash combine seed.
already familiar with how unordered maps work, so I'm not going to delve into the details of why this that it makes in the model vertex reference called other, mark the equal sign, const vertex reference called other,
We model
mark the function const, and then we simply check that all the struct fields are equal. So position equals other.position, color equals other.color, normal equals other.normal, and UV equals other.UV. Then in the model implementation, scroll to the top and include lveutils.hpp. In addition to the equality operator, we need to implement a hash function for the vertex struct, which will make use of the hash combine function we just wrote, but to hash the individual GLM components, we need to include the GLM hash functionality. This functionality is technically experimental and subject to change, so we first need to define GLM enable experimental. But in practice, the GLM library is very stable, so I don't think this is something to really worry about. Then include GLM
is
GTX
maybe this
hash.hpp.
part of it
Finally,
working.
we also need to include unordered map. I am going to inject a hash function for the vertex struct in
Hash include iOS name.
std namespace. So just following the include statements, but outside the LVE namespace, I will add namespace std followed by template angle brackets. Next, we declare a struct called hash with type LVE model vertex. Inside, we need to overload the function call operator. So we have return type size t, then operator brackets, and as the operator function calls argument, we have an LVE model vertex const reference called vertex. And also mark the function as const. Initialize a variable of type size t called seed equal to 0. This will store the arguments seed, vertex.position, and then finally hash it to a single value of type size t, which can then be used by an unordered map as the key. Okay, scroll down, and in the load model function, let's initialize an empty std unordered map, using vertex as the key type and a uint32t as the value type.
Unordered map, unique vertices.
And I'll call it unique vertices. This map will keep track of the vertices which have already been added to the builder.vertices vector, and store the position at which the vertex was originally added. Then scroll down to the end of the function, but still inside the for loops, and replace vertices.pushback with if unique vertices.count of vertex is equal to 0. Then unique vertices at vertex is equal to static cast uint32 type of vertices.size. Then also call vertices
Static cast event.
pushback vertex.
Vertices.
So what this does is if the vertex is new, we add it to the unique vertices map. Its position within the builder's vertices vector is given by the vertices vector's current size. Finally,
Save.
block called indices.pushback unique vertices at vertex. With this, we add the position of the vertex to the builder's indices vector. And that's it. We can build, run, and see our base object once more. The big
What's working now? What did I change? What fixed? Let me check the commits. Okay, when is this game object done? That make a difference? Not IO stream. Right. This is already so broken. Let me check. Was this breaking it? Was not having the IO stream thing breaking it? But why wasn't I getting an error? Yeah, it's working fine. I don't know. Maybe it's a combination of these things. Here we just change this game object. That's it. Here we added this IO stream, which scene does not do anything. Which other ones? Does this? Is it because we're doing the color 0 plus 1 plus 2 thing now? Maybe. Okay, it's working. I'll call it a fix. Fix 3D model loading. Button push. Let's finish uploading. Okay, I'm glad this worked out somehow. Click push. Okay. 18. Diffuse lighting.
Just above in the get attributes descriptions function, we're going to update this method with attributes for the
Model CPP. CD attribute descriptions. Go to messages. Yeah.
and texture coordinates. First, though, I'm going to change how we add the attributes to be more condensed. Update the attributes to use an empty initialization, and then call attributes descriptions.pushback. And in curly braces, we have 0 for the location, 0 for the binding, R32, G32, B32 as the format, and finally offset of vertex, comma, position. Then duplicate this line.
Okay, let's see. Attribute description pushback bracket curly brackets, 0, comma 0, comma, copy this, comma, copy this. Okay, and let's clean that up. Okay, position color normal. Area is only 2. Yes, convey that 0, 1, 2, 3. Yeah.
To be location 1 and the offset of vertex to use the color. In my past experience, I've often caused errors due to making a typo when using the previous, more verbose form, but of course feel free to use whatever you prefer. Then just duplicate this line twice more and update the location value to be 2 and 3. Then change the offset of vertex to use the normal for the third attribute.
Okay, let's Control C, 0, and Control V.
And UV for the fourth. Finally, update the UV attribute descriptions format to only use an R32G32 float since texture coordinates only have 2 components. Next, we need to update the vertex shader. In the shaders directory, open simpleshader.vert and add 2
Okay, open the shader.
lines declaring the vertex input attributes. These attributes will be at location 2 and 3, so we'll have in vec3 normal followed by in vec2 UV. Next, I would
Hmm. Normal UV. Yeah.
push constant definition to define the projection, view, and model matrices all individually. This would give us more flexibility within the shader. We could calculate the vertex position in world space by multiplying the model matrix by the vertex position. For some shader
Okay, let's see. Not for rejection matrix. Wait, let me finish this.
having these intermediate values is necessary, such as when we have a point light in world space, we can use the vertex position in world space to calculate the direction to the point light for each vertex. However, this is where we run into the limitations of push constants, which only guarantee that all platforms support at least 128 bytes. So if we want our code to work on all GPU devices, we can only include at most 2 4x4 matrices in the push constant block. So for today's tutorial, I will instead keep the transform matrix as is, but will remove the color push constant.
Okay.
And add a second map4 type storing just the model matrix. So the first
Model not full. Model matrix.
matrix stores the projection times the view times the model matrix, and will be used to transform our vertex positions. Then declare a const vec3 called direction to light equal to
Transform / projection plus into view into model.
normalize vec3 with values 1, -3, and -1.
Const vec3 light position normalize vec3 and rename this. And so direction to keep it the same, 1.0, -3, and -1.0.
The normalize function is a built-in GLSL function that converts any vector into an equivalent vector of unit length. Whenever doing lighting calculations, you should always make sure that the input vectors are unit vectors, otherwise you will get incorrect outputs. This technique we are using here is called directional lighting, since every vertex, regardless of what its position is, will use the same direction to the light source. This simulates a light source that is infinitely far away from the object. A real-world example of a directional light source would be the sun, since because it is so far away, light rays that reach the Earth are essentially parallel. The alternative is a point light source, whose position would be much closer to the object being lit. In that case, we would need to calculate the direction to the light on a per vertex basis. We will cover point lights in a future tutorial. The direction to the light is specified in world space. Therefore, to properly compute the lighting, we require the normal to be transformed from model space to world space. We can do this by using the model matrix. The map3 function converts the 4x4 model matrix to a 3x3 matrix by removing the last row and column. We only need the upper portion of the matrix when transforming.
Okay, let's get into it. Map3. Let's map3 normal world space. I'll normalize push dot model matrix. Map3 push dot model matrix into normal.
Because they represent directions, not positions, and therefore are not affected by translations. Alternatively, you could also use the full 4x4 matrix and multiply by the normal with an additional fourth component of 0 for the homogeneous coordinate value. But the former method avoids performing unnecessary calculations, so this method of transforming normals by using the model matrix is technically incorrect and only works if certain conditions are satisfied. I will come back to this in just a moment. Finally, we
Let's add the comment also. Temporary only works in certain conditions.
the light intensity at this vertex value. I will add a float light intensity negative, which occurs when the normal is facing away from the light source. When the surface isn't facing the light, we'd like the light intensity to have a value of 0. Finally, the output frag color is given by vertex color scaled by the light intensity. For the fragment shader, we can leave it as is, except we need to update the push constant struct definition. So copy these lines, navigate to simple shader.frag, and overwrite the
Control C, frag shader node. Yes.
push constant declaration with the updated version. Then navigate to the simple render system implementation and scroll to the top of the file. Let's update the push constant data struct to match the shader definition. Then
Simple render implementation. GLM platform model matrix. 0, 0, 0.
scroll down to the render game objects function, and inside the for loop, remove the line setting the push.color and declare new variable with auto model matrix is equal to object.
Auto model matrix equal obj.transform.map4.
.transform.map4. In the line below, remove the map4 function call to use this model matrix local variable instead to avoid performing the calculation twice. And then we have push.model.
Projection view is model matrix.
Model matrix. We can build an
Okay.
and you should see the vase model now shaded with diffuse lighting. Vertices that point towards the light will be lit with a greater intensity, and as the angle between the surface normal and the light direction increases, less light hits the surface and the model will be shaded darker.
Okay, let's run this. Test it out. Yeah, it's building. Well, it's stuck again.
Point away from the light will be completely black. This may appear a little unrealistic. In real life, light bounces all over. It scatters in the atmosphere and reflects off the away from the light will be completely black. This may appear a little unrealistic.
What has gone wrong? No obvious errors. Never rebuild the shadows.
From the, we can build and run to match the shader definition, and overwrite the previous push constant declaration with the updated version. Then navigate to the simple renderer system implementation
Yes,
and
seems
scroll to the top of the
fine.
file. Let's update the push constant data struct to match the shader definition. Then update the push constant data struct to match the shader definition. Then
Let's try running it again. What has broken? That continues.
game objects function. And inside the for loop, remove the then scroll down to the render game objects function and use the shader which the light intensity. I'll come so back to this vertex value. I will add a float light intensity is equal to the dot product of my normal in world space, comma, the direction to the light. Now it's possible to have a value of 0. Finally, the output frag color is given by vertex color scaled by the light intensity.
Yeah, light intensity
For the
into
fragment
color.
shader, we can leave it as is, except we need to update the push constant struct definition. So copy these lines, navigate to simple shader.frag, and overwrite the previous push constant declaration with updated version. Then navigate to the simple renderer system implementation and scroll to the top of the file. Let's update the push constant data struct to match the shader definition. Then scroll down to the render game
Okay.
objects function, and inside the for loop, remove the line setting the push.color and declare a new variable with auto model matrix is equal to object.transform.map4. In the line below, remove the map4 function call to use this model matrix local variable instead to avoid performing the calculation twice. And then we have push.model matrix is equal to model matrix. We can build and run, and you should see the vase model now shaded.
Was that the error? The light intensity wasn't used? Oh, that's wrong. I'll check the comments. M uses 256 bit by SIMD registers. Completely white space just suits me fine.
With diffuse lighting. Vertices that point toward normal and the light direction surfaces that point away from the real life light bounces all, even the darkest, because even in complete deep void of space, where there's nothing for light to bounce off of, indirect illumination. Unfortunately, accurately modeling indirect illumination is very, very hard, especially for GPUs. The ambient
See, couldn't apply directional sort inside the fragment shader on the main function. Fragment shader instead of doing texture, frag types, coordinates. Could we put normals instant and how come we went for vertex shader based lighting algorithm as opposed to a fragment shader?
lighting model is a very simple way
After we're missing something, let me try just closing and opening C line, see if that fixes anything, because that has worked before.
the direction to the light is specified in world space. Therefore, to properly compute the lighting, 4x4 model can do this by using the normal source, the Earth, R, since equivalent vector of unit length. Whenever doing lighting calculations, you should always make sure that the input vectors are unit vectors, otherwise you will get incorrect outputs. This technique we are using here is called directional lighting, since every vertex, regardless of what its position is, will use the same direction to the light source. This simulates a light source that is infinitely far away from the object.
Let's see this also. 17, 18. Shadows, simple shadow load. Location 3. Vector UV. Prefab color uniform push. Transform. You're doing model matrix. Match node 0. Math3 push. Model matrix normalize. Let's finish the whole thing and then go back.
We can use the vertex position in world space to calculate the direction. The offset of vertex to use the normal for the third attribute.
Let's just run it and see. Okay, the window showed up quickly, but like nothing else worked. Test float, test float. see LV model. VK format. Offset off, offset off.
and UV for the fourth. Finally, update the UV attribute descriptions format to
There are no like stash on shelf changes. Let's close that. Let's play again. See if it works. Okay, it's working. Unshelf. Okay, we're not. We're getting the call from there. Let's try running it. Okay, it's recompiling the shadow. Color, out color.
G32 float, since texture coordinates only have two components. Next, we need to update the vertex shader. In the shaders directory, open simple shader.vert and add two more lines declaring the vertex input attributes. These attributes will be at location 2 and 3, so even the darkest part of a shadow doesn't appear completely black to our eyes. And that's because even in complete shadow, some light indirectly reaches that location. It would only be in the deep void of space, where there's nothing for light to bounce off of, would you get a completely black shadow. This type of lighting is known as indirect illumination. Unfortunately, accurately modeling indirect illumination is very, very hard, especially for GPUs. The ambient lighting model is a very simple way to roughly approximate indirect illumination. It assumes that every object receives a small, constant amount of light from all directions, regardless of what direction the surface is facing. Back in the simple shader.vert, I will add a const float value called ambient, and set it to a small value such as 0.02. Then in the light
In the bot, const float ambient equals 0.02.
calculation, I will add this ambient term to the current calculation so that all vertices receive a minor
Ambient
direct illumination. Now, if I build and run, the base model looks a bit more realistic, since even the portions of the model not facing the light still have some amount of lighting applied.
Let's see what happens. Transform one.
If all vertices receive a minor
Image. Let's making this 1.5 on-offs. Doesn't appear to be fixing the problem. Yeah.
Illumination, since even the portions of the model not facing the light still have some amount of lighting applied. Along with the smooth vase object, I also provided a second object file called flat vase that you would have downloaded in the previous tutorial. So if you navigate to your app implementation, we can change to using this object file instead. First, I will adjust my object's translation in the Y direction to move it down by 0.5 to have the model a bit more.
First, flat. 0.5.
Instead, load model / flat vase.obj. When I build and run, the second vase object has a much more faceted appearance, where each face of the vase is clearly visible. The difference between these model files is based on how the vertex normals were calculated. The smooth vase object uses vertex normals.
It's clear. Okay, buffer.
Also known as smooth shading. This is when the normal at each vertex is calculated as if there existed an underlying smooth surface. The flat vase object uses face normals, also known as flat shading. This is when the normal at each vertex uses the same normal as its face. Face normals are more commonly used in low poly art styles, when you want each individual polygon to be clearly visible. Since a vertex can be shared by multiple faces, this means we will have duplicate vertices, one for each face. Because of this, a flat model will have more vertices than its smooth model counterpart. You can choose between flat and smooth shading in Blender before you export your model. If you select your model in object mode, and then open the object drop-down menu, there should be two options, shade smooth and shade flat. Select your desired option, then go to File, Export, Wavefront.obj. Before exporting your model, you will likely want to adjust a few settings. First, under the transform heading, you should set the transformation to match the coordinate system convention that your engine is using. In our case, that means positive Z for the forward direction, and negative Y as the up direction. Next, in the geometry menu, you will want to select the triangulate faces option. You can optionally choose to include materials, but we're not using them currently, and then also have right normals and include UV selected. You can save this as a preset if you wish to make future exporting quicker. Transforming normals isn't quite as straightforward as simply multiplying by the model matrix as we've done so far. This calculation is actually if uniform scaling is being performed. This means that the X, Y, and Z directions all apply an equal amount of scaling to the object. If you change the scale factor on the vase object to squish the model vertically, and then render it, you can tell this doesn't look quite right. The image looks as if I took the previous vase object and simply squished the image of it. The proper way to transform normals is to use the inverse transpose of the model transformation matrix.
Okay, let's see. X3 normal notes.
The vertex shader. To instead use the inverse transpose and re-render, we can see the
Say map 3 normal matrix or transpose map 3. Yeah. That was yeah. Transpose dot inverse map 3 push map 3 push dot model
It's interacting with the light correctly. I'm not going to prove here why this is true, but I provided a great resource that
That intensity normalize.
now looks as if it's the light correctly. I'm not going to prove here why this is true. Need to be transformed differently. But now we actually have another problem. Computing the inverse of a matrix per vertex within a shader can be computationally expensive and is typically not recommended. So we have a few viable solutions here. One, change your engine to only allow for uniform scaling. So scale becomes a float that acts on the x, y, and z components equally, and can just use your model matrix on all your normals. This is actually a very commonly used solution by game engines. Option 2, compute the inverse transpose on the shader, which is not recommended for performance reasons. And option 3, compute a normal matrix on the host and pass it into the shader. I'm going to use the third method here, even though it has the disadvantage of adding extra complexity to the engine.
Some pre-computed normal matrix.
But if you know that non-uniform scaling is something you simply don't care about, option 1 may be the preferable choice for your engine. Constructing the normal matrix directly is actually not very complicated, so we can avoid most of the computation costs associated with using an inverse function. First, the normal matrix will only be 3 by 3 and can ignore the translation component since only position values are affected by translations. Therefore, the normal matrix is given by the inverse transpose of the rotation matrix times the scale matrix. Using a bit of linear algebra knowledge, we can rearrange this to get the normal matrix is equal to the rotation matrix times the inverse scale matrix. The inverse scale matrix just uses the reciprocal of the scale factors, so we can easily
Okay, and the watch. Shape function of 6. Shift F6. Shift F6. And this is normal matrix. See, here it's social model matrix.
result of the push.normal matrix times the
Normal world space.
copy the push constant definition and overwrite the push constant struct in the fragment shader so that they match.
Yeah,
times the vertex.
okay, we have that. Shift F6. Yeah. Normal matrix.
Copy the push constant definition and overwrite the push constant struct in the fragment shader so that they match. And then in the game object add a new function to calculate the normal matrix. First though, let's actually move the function implementations out of the header to an implementation file. So I will create a new file called lvegameobject.cpp, including the lvegameobject.
Yeah. Here lvegameobject CPP. Game object HPP.
HPP header file and then add my namespace. Back in the game object header.
Hash include lv game object HPP namespace brackets lv
We'll copy and remove the map4 function's body, so that just the map4 function declaration remains in the header.
Cannot for Control C.
Game object implementation. Paste the function body in and add the transform component class name scope before the map4 function's name.
Transform component.
And then back in the game object header,
GLM map4 transform component map4.
I'll declare a new function that returns a GLM map3 type called normal matrix. In the implementation
HTTP. Okay, let's see. GLM map3 normal matrix. Packets.
the GLM map3 transform component normal matrix function
GLM map3 transform component normal matrix. There we go.
and then I'll copy the contents of the map4 function to use as a starting point. Declare a new local variable of type const.
Control C, Control V.
Called inverse scale and set it equal to 1 over scale.
Points GLM vec3 inverse scale 1.0 f.
Change GLM map4 to return a GLM map3 object type.
Scale
Remove the last component from each column vector, as well as the entire last column. Then change each occurrence of scale
map3.
Y or Z to instead use the inverse scale local variable. And that's it. The normal matrix
And let's do Control, no, Shift. Let's copy this. Yes. Yes. paste. And remove this. Okay.
Except it's 3 by 3 component and scales each column by the reciprocal of the scale components.
Note, I'm actually not sure if directly computing the normal matrix is faster. I'm simply using GLM to calculate.
In the simple render system implementation, we can rename model matrix to instead be normal matrix. Then in the load
Okay, simple render system. Shift F6. Normal matrix.
set push.normal matrix equal to object.transform.normal matrix. We can't
Object dot transform dot normal matrix.
the project yet because there's a mistake in the vertex shader. The normal matrix is 3 by 3, not 4 by 4. However, in our push constant struct, we will still use a 4 by 4 matrix because of alignment requirements. I covered alignment requirements in tutorial 9 when I first introduced push constants. And mat3 is actually 3 vec4s, as each vec3 is 3 floats aligned to 16 bytes. So at least the easiest way I know of to pass a 3 by 3 matrix to a shader with the proper padding is to pass it in as a mat4. And then when you want to use the matrix within the shader, truncate it by using a mat3 conversion. So wrap push.normal matrix with the mat3 constructor before multiplying it by
Mat3. Okay.
vector. When we initialize the push.normal matrix in the simple render system implementation, the GLM library will automatically convert the 3 by 3 matrix returned by the normal matrix function.
Match.
So wrap push.normal matrix
Normalize mat3
with the mat3
push.
constructor before multiplying it by the normal vector. When we mat3, and then when you want to use the matrix, at least the easiest way I know of, in as a mat4. And then when you want to use the matrix within the shader, truncate it by using a mat3 conversion.
Okay, he was just doing a direct multiply.
So wrap push.normal matrix with the mat3 constructor before multiplying it by the normal vector. When we initialize the push.normal matrix in the simple render system implementation, the GLM library will automatically convert the 3 by 3 matrix returned by the normal matrix function to a padded 4 by 4 matrix.
Yeah, maybe that was the
Build
issue
and run,
before.
and you should see the switched bays once more with the correct lighting.
Let's try it and see. Oh, what is that? Has it crashed? Some weird way. Yeah, this is still not working. Let's see in next chapter,
So, as of
episode.
the last tutorial, we've come up against some of the limitations of push constants, namely the limited space. For more complicated
Do they fix
shaders,
any
we would
of
like to be able to
these?
provide more data. To do so, we will use a uniform buffer. A uniform
No. What has broken this time? Look at all my changes. Let me check here. Says 18. Okay, I will be model CPP. Hmm. Okay, 0, 1, 2, 0, 1, 2, 0, 1, 2. What has changed in this? Let me try making this direct. First, and Control C, Control V. Okay, it goes color, normal. And then UV, air, 1, 2, here. Hmm. Okay, let's play. See if this works. Okay, slightly different screen. That's good news. See, now some comment. Hmm. Location binding. This is like no progress, I guess. Why does the pushback not work? Control F, push back. Well, let me try this. Control D. And place back. Let's copy, paste, and place dark. Cannot resource in place. Okay, let's try this and see. Hmm. Building, and it's getting stuck. Okay, let's delete those and go back here. Two and three. Let's try this. Okay, so last. Okay, there's no lighting on it, but I've made some progress. Oh, let me Google search and see. Review pushback not working. Vector pushback function not working. And this 15. There are two bugs on line 12. Let's see if ChatGPT can get some answers. Why thus not working? Text. Now parameters under an order. Just assume nothing is broken. For whatever reason. Okay. Now let's go. Then also change now. Will what we change this to normal matrix. How do I refresh? Oh, just like saves it permanently. Okay. Model anything else? No. First off, smoothies, flat waves.
Being applied. You can even render both the smooth and flat phase models at once. All it takes is creating a second game object. The load game objects function, set push.normalMatrix equal to object.transform.normalMatrix.
Okay.
That returns a GLM mat3 type called normal.
Okay, show vertex. Like this animation value.
Shader. The normal matrix.
Let me go here. Hmm. Oh, this is under shading. Okay, UV, frag color, push, transform matrix, normal matrix, 1 minus 3 minus 1, 0.02, push, transform, vec 4, position 1.0, normalize math 3, gets math 3, normal, and ambient max dot normal versus direction to light, 0, light intensity into color. Fragment, normal matrix, uniform push, color 1,0. Okay. First tab CPP. Mm, yes. Specify. Specify. Okay, let's remove. Let's load it and see what happens.
Is 3 by
Is
3,
there some
not 4 by 4.
extra stuff?
However, in our push constant struct,
Let's make sure this is running at least. Right, exit. Let's play it again. Okay, the crash was weird, but whatever.
we'll still
Okay.
use a 4 by 4 matrix because of alignment requirements. I covered alignment requirements into
Okay, besides that, okay, next we this one. Okay, object CPP. Okay, let's see. This one is fine. GLM Mac 3, Vec 3 inverse scale, 10F scale, return GLM Mac 3. Semicolon. Let's see if that extra comma is breaking anything. Shouldn't, but yeah. Why is the lighting not applying? Checked HPPP, deleted all of that. Comparative and rotation, not for normal matrix. And nothing else over there. Okay, this one I checked. Now, simple render system. JLM Mat 4, Mat 4. Okay, auto model matrix, object.transform.mat 4, project view into model matrix, normal matrix, object transform model matrix. Which part is breaking?
Tutorial 9, when I first introduced push
The Sheldon can go delete. Okay. Shadow, vertex. Hmm. One minus three minus one. Yeah, those values are correct.
constants. The mat3 is actually 3 vec4s, as each vec3 is 3 floats aligned to 16 bytes.
Smooth. smooth object.
At least the easiest way I know of to pass a 3x3 matrix to a shader with the proper padding is to pass it in as a map4. And then when you want to use the matrix within the shader, truncate it by using a map3 conversion. So wrap push.normal matrix with the map3 constructor before
Let me try not doing that. As plus in the word shadow. My photo is like this.
multiple matrix within the shader, truncate it by using a map3 conversion. The matrix within the shader, truncate it by using a map3 conversion.
Push to normal matrix into normal.
Push.normal matrix with the map3 constructor before multiplying it by the normal vector. When we initialize the push.normal matrix in the simple render system implementation, the GLM library will automatically convert the 3x3 matrix returned by the normal matrix function to a padded 4x4 matrix. So now we can build and run, and you should see the switched base once more with the correct lighting being applied. You can even render both the smooth and flat base models at once. All it takes is creating a second game object that uses the other model file. If I do this,
And game object.
shifting the flat phase slightly left and the smooth phase slightly to the right, I can build and run and compare the two phase objects. The vertex
0.5 minus LVE model. Game object model. Shift F6. LVE model. Save.
all the same.
Shift F6 is flat is versus smooth is.
Shader is used by both. The only difference is how the model files specify the
Let's load it up. Flat is, smooth is. Why is the lighting not getting applied? Let me try just restarting C-line. Sometimes that works.
I'll clean up this unused code in the vertex shader. And that's it for today. Thank you for watching.
Light. Hmm. Like 3, then back 4 position. Back 3 float fraggle. Normal matrix, push, push. Back 3, back 3, back 3, back 2. Little Vulkan engine. Lighten, working. Episode 18. I've also tried with and without the index buffer, same result. There's a proper configuration of VK pipeline that stencil create infrastructure. Let's see what other people have done. Okay, this is just copy of this. This is just a fork. I think it is. The file paths are fine. Let me check. Yes. Tutorial 18. Oh, it's just the same as Let me check on Google. Hmm. Let me try checking here. What point do they end the vertex buffers, I guess? Not as drawing a triangle, this is uniform. Buffers, loading models. Texture, images, uniform. myself. Well, let's see. I'm just asking and see. Why is the lighting not being applied to the game object? Hmm. Push console message. Model has it written so much. Lighting calculation of show the ambient light. Let's just remove this ambient light altogether. Let's see what happens. And it crashed. Let's try again. Crash again. Let me not touch anything. Select it and then move it about. It's fine. If I leave it, crashes immediately. Model matrix. Transform position to clip space. I don't need this for now. Normalize light direction. Normal world space. And I'm missing something there. What? Normalize battery. Yes. Max dot normal world space direction to light. Let me make it 0.0. Let's see if that matters. No, it does not. What could be the issue? Update the render system to pass the view projection matrices separately. Hmm. Projection view model methods. Projection view into model matrix. Bind all of this push. This can be closed. Nothing helpful under here. It should just be a direct apply. What is going wrong here? There are other methods that can help reduce duplicate vertices. Vulkan has something called provoking vertex, which uses one of the vertex normals as a normal for the entire face. And the beta in the fragment. The dark side remains dark even while rotating. Now we will turn inside out. And the pipeline implementations. Check your clip settings. Control F. Clip. Cons flow 0.12. Let me try this. Try to now. Still crashing very randomly. Might have to fix up whatever is issues in. Now just it go into a crash. Let me leave it. Let it load up. Still not getting lighting. It's only the ambient lights that's there. Hmm. Let me try just copy pasting the code. AV pipeline. Let me try checking the model work. Copy all of this. And as model CPP. Control C, Control V. Let's try. What was the issue? What? Okay. Clearly something changed. Ah, was it this? Is this supposed to be 4? Oh my gosh. Let me change this. Okay, city vertex. Okay, let note this. And over here, like this, like this. Let's see if this works. Okay, that was the issue. Um, at last we solved it. Okay, and delete all of these. And now save everything. Yeah, diffuse lighten. I'll just run it one more time just in case. Okay, everything is working correctly. Okay, nice. Commit and push. Just that one thing had to be changed. Push. Now, should I do the uniform buffers? No, the guy to clean our house is coming, so I'll do that tomorrow, and I'll do this descriptor sets as well. Okay. Okay. I'll see all of you all tomorrow. Bye.